So let's get started.
Woohoo! Thank you for waiting on me.
So last week we mentioned the mean trend, okay, the trajectory of different types of growth. And then we also talk about homework 2. So we didn't cover the, let's just talk about the choose a number of factors, because last week we invited some students come here and you can choose 2, you can choose 3, you can choose 4. So they are here, these are suggestions, okay? So first, you can just consider some, at least you should read some literature about that area. So consider some prior hypothesis or theory about the number of factors. So for example, some other people has already done the research and he suggests 3, then you might consider 3. It's kind of like the range, the rough number of factors. And you're gonna also consider rule of thumb, for example, script plus, okay? And get some idea. So what's the range? What is the number of the rough number of the factors, approximation? And then you can also do the decomposition of the covariance matrix, Kaiser's rule or cumulative eigenvalues, parallel analysis, and Jachi, okay, did all of this, and he also computed the cumulative eigenvalues, and he said that there are 6 will be the yeah. So based on Kaiser's rule, we have 2. Okay, based on the cumulative eigenvalues, we have 6. So all of these are a possible number of factors. And then you're gonna also consider the results. Okay, you can just run 2 or 4 and then look at the factors, the results, and the measure. Okay, measure factors, and also you should do the you do the interpretation. So what's the meaning of those factors? Okay, so if you just group some items together, so what are these items are going to measure? So you also need to consider the interpretation of factors. And then consider some model fit. Trying to use different rotations, okay? Rotations, orthogonal or oblique. And suppose that the model fits well by using n factors, then you're gonna check a little bit different. For example, if you check a model with n-1 factors or n+1 factors to see, okay, if this model with n-1 significantly worse than the model with n factors. Or you can try the other model, okay, with n+1 to see if that model fits significantly better. And
So on this last homework that we just did, when you were asking about model changes and stuff, this is kind of what you were alluding to in the question, correct? On whether it's the saturated or nested or how many factors you got. That's how I explained it.
Yeah, so in your course project, you're gonna use these techniques.
Okay.
Yeah, you're gonna use these solutions or suggestions, yeah.
Okay, thank you.
So, yeah, so all of these are suggestions. So the final decision is based on a combination of your theory, okay, your data, the collect data, model fit, interpretability of factors, and also parsimony. Okay, so you're gonna try to keep your model as simple as possible. Of course, you're gonna choose the best model. Okay. So those are some suggestions for you. And also those are, suggestions from EFA. Okay. And this week we're gonna move forward to multiple group analysis. So we're gonna try to look at the model estimation and the test group difference. So we have different groups to test where's the difference. Okay. And we have some examples. And session 2, we're gonna extend or apply this multiple group analysis to measurement invariance. Okay, so that's for session 2. So let's look at the review slides. This is a general SEM when we assume the intercept is 0. So without considering the mean part. So we have 3 equations: X measurement, Y measurement, and the structural models. Okay, so everyone should be very, very familiar with these 3 equations. But if we consider the mean part, then we have the intercept part. Okay, so mean of x, mean of y, and the mean of the eta part. So these are the covariance part. We also have the mean part. So combine them together, it's a SEM. Okay, we have 3 equations for SEM, 2 measurement models and 1 structural model. Now, so previously we just considered one group. Now let's extend it to multiple groups. Okay, multiple group analysis. So we have a sub G. So this is for the model without mean. These are models for considering means. So we have a new sub G here, each of these. So what does that mean? For each group, this might be different. For example, for group 1, we have equation. For group 2, we have x measurement. For group 3, we have different. So these dramatically increase the number of equations. So, for example, for male and female, the measurement model, the Y measurement model, or the structure model could be different because they belong to different groups. Okay. But some people also argue that, okay, I understand you can compare multiple groups, but why not just add that grouping variable as a new covariate? For example, we're gonna compare female and male. It's another possible, okay, it's another solution that we can just add the gender as our covariate. When gender is 1, for example, it's female. When gender is 0, it's the male. Then we're going to see the difference among these 2 groups. So that's another possible solution. So multiple group analysis, one approach, a single group analysis with covariate, the grouping variable as our covariate. This is another solution. Okay. So if we do a comparison between these 2, then, so multiple group analysis might be better than the other approach, okay, because it's more flexible in investigating differences in factor loadings, variance, covariance, means, and intercepts. Because we can make all of these components different across groups. But if you just add a covariate with that grouping variable, so that the difference cannot be, okay, the model cannot investigate the variance, covariance, or other. Let me see, factor loading, is that possible or not? Maybe mean and the intercepts are possible, definitely possible. But it depends, okay, it depends where the component of the covariate. So multiple group analysis is more flexible. You can do all of this comparison. And requires a larger sample size for each group. Okay, so yeah, this is true. So if you have multiple group analysis, that means you have to increase your sample size. You have to make sure, so you have multiple groups, you have to make sure there's enough sample size for each group. Okay, that's maybe the limitation, okay. And it's not easy to carry out many groups. So if I say, okay, 2 groups, 3 groups, that's okay. But if you say, okay, I have 100 groups, that's not possible to just run the multiple group analysis, because I will show you the code. I will give you the code. You can see that if we have some limited number of groups, then it's easy for us to handle. But if you have a large number of groups, then at least the number of parameters will be dramatically larger than in a single group analysis. So we have pros, we have cons for multiple group analysis. Okay, so there are some limitations, but we also it's also very flexible. So let's look at the model estimation based on the SEM. Maximum likelihood description function. Okay, so if we consider the covariance part and the mean part, okay, so from here to please ignore the summation. Summation means, okay, so for each group, I'm gonna calculate the mean part, the mean part and covariance part of the function. Okay, inside the brackets, it's each group's FML. And then for multiple group, I just use the sigma, okay, capital sigma, to show it's a sum. So within the sum, let's look at the within the bracket. So you should be familiar with this part. So from here to here is the covariance part. Okay, so when we talk about the covariance analysis, so we use that F function, FML function. And then from here to here, it's for the mean part. So we have the sample mean, we have the model-based mean. So this is the inverse of the model-based covariance matrix. And also we have the mean part. And then here, this is the model-based covariance matrix. This is a sample-based covariance matrix. So combine them together. Variance part, mean part for each group. And finally, we need to add all of these function values. Okay, so actually, I didn't use a sum. So the capital sigma should be like this. So I omitted some notations. G should be starting from 1 to capital G. Suppose capital G is the number of groups in this case. So inside of the brackets, all of these are, okay, so we have sub G, okay, so we have some S, and we have M, we also have mu. So for different G, for different groups, we have their specific function. And then we add them together. That is FML for multiple group. Okay, the sum of all FML. What is the degrees freedom? Just like the single group analysis. So we know that sample size times that FML follows a chi-square distribution. This is a statistical asymptotic distribution. Okay. So this value, sample size times this FML follows a chi-square distribution. What is the degrees freedom? This is a degrees freedom. Again, this should be a sum. The sum of this is for each group. Okay, so we have P, number of variables. Okay, Q, number of parameters. So we have the degrees freedom for each group, and then get the sum. That degrees freedom is an FL for multiple groups. Okay. So then, when we do, of course, you need to do the maximum likelihood of the estimation. Okay, so after some iterative algorithms, so all of these are functions of unknown parameters. Theta is a parameters. Okay, all of these are functions of our parameters inside this form. So after we got the convert result, then we have the parameter estimates. So if you want to do the test, if a parameter is the same cross groups, you can consider like the nested model. So one is a full model, the other one is a model with constraint or a reduced model. And then because chi-square difference test gonna tell us the difference between two models, nested models. And then we're gonna see, okay, if the difference is significant or not. We have a full model, we have a reduced model. If it's significant, that means the reduced model is significantly worse than the full model. We should use a full model because the reduced model, by putting some constraint, is worse, is significantly worse. We should not use it that. Okay, so keep the full model. If it's not significant, then based on the parsimony, so we should keep the simpler model. Okay, we should use a reduced model. Okay, again, the theory is the same as, or the logic is the same as a single group analysis. So just do group comparison, chi-square difference test. And we can also consider, we should also consider model identification, okay, estimation testing and modification. Yeah, so all of these techniques are quite similar as a single group analysis. So let's look at the older data. We use this data in previous SEM models. Now we have two groups, male and female. So we still use the HBLTT, okay? So it's for memory test. LSLT are measure of reasoning abilities, and EPT is our dependent variable, measures a participant's ability to solve problems associated with daily life. So all of these are the same as before, but now we include a new grouping variable, gender, male and female. And we also consider the mediator. Okay, this should be a mediator. And the reasonability, this is a latent variable, okay? Latent variable of these three, okay? This is a factor of these three tests. Yeah, question.
Sorry, I'm not trying to make this a tangent, but in a lot of the survey building classes, they discourage when doing surveys and stuff like this for using just the two groups. You always have to have an other or not declared. So
yeah, sure. If you want to add other groups, that's totally fine.
okay.
But the number of groups should not be large.
Right.
If you have 5 groups, that's fine.
Because what people identify as today, you have to give them options of what to identify as.
That's fine. Yeah, if it's but you have to make sure those options are mutually exclusive. You cannot say, okay, I belong to this group and also at the same time I belong to the other group. No.
Only one answer. Okay.
Yeah, just one answer. And then this model applied.
Okay.
Doesn't matter 2 groups or 3 groups or 5 groups. Yeah.
Thank you.
Yeah, great question. Yeah, great notation. Okay. Okay, so this is a code. Let me just explain this a little bit.
Like 7.
Yeah. So you can see that the code has different parts. Okay, so the first part is quite similar as before. And then here we have a new statement, grouping. We add a new grouping variable here. That's very important difference. Okay. A variable called gender is in our original data set, and we have 2 outcomes. Okay. 1 is male and 2 is female. And then starting from here to here, those are models. And before that, we have here, this is a very, how can I say that? This is a very important revision, because when we talk about the fact analysis, some people came here to ask me, can we just use the average of tests to do the data analysis? Previously, we said, okay, R is a latent variable of these 3 items. So these 3 are indicators. And then we extract the R from fact analysis. That's a great approach. So let me just show you. Previously, we used this model. So we have WSLSLT. We assume that there's a latent factor which influence these 3 reasoning tests. And we have different lambda value, okay? Lambda 1, lambda 2, lambda 3. This, if you go back to check, these lambda values are different because the inference of the inference of the reasonability on these 3 tests are different. But this is very good. This is a scientific way to run the data analysis. But currently, a lot of people, okay, so especially social and behavioral research scientists, they just don't care about the effect model. They just take the average of these 3 tests and assume there's a reasonability, okay? Assume this reasonability is just average of these 3 tests and just run the data analysis. So they got published. So how can I say that? This approach is not good as a fact analysis, but it's still very popular. People are doing that.
Just because they succeed doesn't mean it's right.
But they got published. So anyway, so this is another new approach. So I think that maybe it's also mentioned to we can also mention this approach here. So let's define a new variable called R. So R is not here. So when we look at the names, there's no R because R is not directly observed. In fact, analysis, we created R by using the EFA or CFA. Here, I just directly define R is a mean of these three tests. It's very popular. So you can do it this way. But of course, I prefer the vector model because you know what? So suppose the vector loadings are quite different. This one it's really large and this one is really small. So if you treat these are equally weighted, then it's not fair for some items. Because when you consider mean, so you think all of these have the same value, okay, the same vector loading. So the inference from here to here, it's quite the same. So that's why we use average. Average, we just consider the weight of 1/3 for each item. But in most cases, those lambdas are not so balanced. If it's balanced, it's fine. It's roughly the same. But if the lambdas are not so balanced, and then you treat the weight is 1/3, okay, equally distributed, it's not fair for some items. But anyway, again, it's doable. So let's just use this way. Okay. This is a new variable. It's average of 3 tests. And then let's look at the model. This is the model, the previous model. Okay, so R on HEDU, HVLTD. So it's our mediation model. So we mentioned the model a lot of times. So let me just repeat it again. So it's a mediation model. R on HEDU, okay. H here, EDU here. And we have variance, covariance. And we have HVLTT test. And we have R. Okay. Now R is not circle anymore. It's a square because it's a sum, not a sum. It's an average of 3 observed values. So it is observed. This is not latent. So we have 3. Okay. And it seems that based on the code, okay, so HVLTT on. So this will inference these 2 are on these 3. So we use a previous model. So that means that this is a modified model. So that means the reasonability of that person will be inferenced by age. That makes sense. Okay, different age. Then the reasonability will be different. Also the educational level. Okay, so with different education. With different years of the education, the reasonability will be different. And also the memory effect. Okay, so memory gonna influence the people's reasoning ability. So this is the meaning of this test. So this is a modified model in the modification lecture. So we just adopt that model. And then we have EPT. Okay. EPT is all of this. Okay. So inferenced by age, inferenced by EDU, inferenced by memory ability, inferenced by the reasonability. In this case, actually, you can just erase this because it's just average. Okay, just a new variable here. And that's the model. Okay, so starting from here to here, nothing new. It's just our previous modified model, mediation model. That's it. But now let's see, we have something new. Model female. We just repeat this part of code. Okay. This is the original model code. And then we said model female and repeat something here. So what does that mean? So I'm gonna do multiple group analysis. Okay. So from female and male, so we have 2 groups. All of these parameters could be different. Okay. And then we have the mediation effects. Okay. EPT, IND, EDU, okay, EPT, INDH. So from EDU education to EPT, all the possible indirect effects. from age to EPT, okay, all the possible indirect effects will be reported if you have this option. Yeah, so let's try to have exercise. Let me give you the code. So here, see. This is the data. So we have the original data. So the data is like two groups. Okay, active data. Okay, so download the code and the data and the OpenStack Plus.
Bless you. Bless you.
Ew.
Bless you.
So we're just trying to open the. Okay, so let me make it a larger. Okay, so this is the original data set. So we have. So we are not going to use twin, and then we're gonna use this. Okay. So let's see. Yeah. So this is the code. The first column will not be used in our model, but we needed to include gender, age, ED, HBLTT, EPT, and C here, okay? WS, LS, LT. Oh, we also have LTV. Okay, these three are not included in our user variable because after taking average, I don't care this retest. I define this new variables, so LS, WS, LS, LTV, okay, were not included in our model. So these are not in the user model, but instead I'm gonna use R. R is average of these three. Okay, so this is different than the previous code. So here, these three are not included in the user variable. Instead, we have R. And the grouping variable, okay, so here we have gender. So in the original data set, we have gender. So gender is included. So gender is not shown here. There's no variable called gender in the model. But, okay, so we have a statement to say that gender is our grouping variable. So this is a default. This is a default keyword. You cannot change this word, okay? So it's grouping, and you put the gender, and you're gonna clearly see how many groups, some outcomes, and the meaning of this.
So that's going to group them into male and female before it runs the model test. So you'll have a model for male and a model for female, right?
That's the meaning of this code.
Yeah.
But you can also keep most of the same and keep some different. I will give you, I will
Sure.
give you.
I'm just following along.
Yeah. So let's see the original data set. So we have gender is the second column is gender. So we only have 1, 1, 2, 2, 2, 2, 2. So if you have multiple groups, you can add a 0 or 3 or 4. Yeah. But in the code part here, you're gonna state here. Okay, so if you suppose you have 3 groups, then you have suppose it's 0, then 0 means whatever, and 4 or 5 means, and yeah, so that's it, and that's it. So let's try to run the code in M plus. So it's wrong. Let's look at the result. Let me just make it larger. Okay, we'll repeat part of input file. And then here, okay, so here, number of groups previously, okay, without including the statement of grouping. So it's always 1. Number of groups. Now we have 2. If you have 3 groups, 3 categories, you have 3 or 4 and it's 4. Okay, it's different now. And then number of observations. So for each group, we have male and female. Okay, male, we have 257. So it's quite smaller than, this number is quite smaller than the female, but it doesn't matter. Okay, so for female, we have 857. Total, this is the total sample size. Okay, so previously we know the total sample size is 1,114. Number of dependent variables 3 because we have EPT and we have HDLTT. We have R. Okay, so these are 3 dependent variables. Okay, observed dependent variable. See, the R here is observed variable. R here is not latent. It's observed because it's just a function of observed variables. It's just function of the mean. Okay, it's average of 3 variables. So it is an observed dependent observed variable. But in previous models, R is always defined as latent variables. So here, number of continuous latent variables 0. In this model, we don't have any factor models involved. So you can do that. Number of independent variables 2. So we only have EDU and H. Okay, so we have 2 independent variables. And we have a new variable, okay, gender, okay, grouping variable with special functions. And we have the different evidence, data, descriptive statistics, okay. All of these are descriptive statistics. And then model fit, okay. And model fit. Look at the model fit. Can you tell the difference? How about this model? That's what, based on the output here.
I mean, it's perfect.
Yeah,
Yes.
CFI.
Do you know why?
One, yeah.
Do you know why?
Because you probably have a variable in for this ID or something like that.
Because there's no latent variables. All of these variables are
Oh.
observed. If you run mediation or moderation, you will see those model fit is perfect, it's saturated. Okay, so
I was gonna say it's
So it's
saturated because the degrees of freedom is 0.
no, it's not saturated. Okay, but there's no latent factors. So, model result. Okay, so we have the result table here. Are on these 3. Okay, so all of these parameters are estimated here. Are on that RH is negative. Okay, it's negative, so that makes sense. So with a larger number of H, the R is smaller. Negative 0.163, and it's significant. Okay, and the R on EDU is positive. Okay, this one is positive. Is 479. It's also significant. On HVLTT, this one is positive. Okay, that also makes sense. With a higher level of memory ability, then your reasonability will be high, and also it is significant. So that's okay. Before that, notice that is group male. So here, this result is only for group male. Okay, because we have 2 groups. Let's do some comparison. Okay, so for group male. Let's just write it down some values here. And then HVLTT on H. HVLTT on H. So that one is negative. It also makes sense. Okay, with a higher value of H, the memory ability will smaller, decrease. Okay. And EDU, this one is positive. This is 596. Okay, so with a higher level of educational level, the memory ability will be higher. Okay, so again, this is for male group. And we have other path analysis, EPT on H, and the EPT on EDU, EPT on R, EPT on HVLTT. So all of these 4 paths are estimated here. Okay. And this one is not significant on H. This one is not significant from H to E. This is not significant. Okay. Others are significant based on the result here. And covariance. Okay, this is covariance, mean part, set part, and the variance of the residual. Okay, so here the residual variance. So for HVLTT, for R, and for EPT, we have residual variance. Okay, now next exciting part. Okay, group female. We have another group. Group female. Let me just move it a little bit. Okay, so this part is for group female. So what's R on H? R on H. It's different. Okay, so for male, it's this number, R on H. I just copied it. It's negative 0.163, but now it's negative 0.139. It's also significant.
It's because women never forget anything.
No, this number is larger. Male keeps forgetting. Oh no, this is not memory test. This is for reasoning test. The age will have big influence on the reasoning ability. So get older. So for male, okay, get older. If it's older, then the reasonability will be smaller. Okay, for female, it's better. And R on EDU. So for male, it's 0.479. For female, 0.498. It's quite similar. Okay. HVLTT, it's also quite similar. Okay, all of these are significant. And the HVLTT on H, it's quite similar. Memorability is quite similar. Reasonability is not. Okay. And EDU, EDU, it's also different. Oh, I'm sorry. So for male, it seems better, okay. But for female, is lower than, but still, it could be similar because we can do the test, okay. Later on, we can just test if this test and the number is significantly different or not. And the EPT on age, okay, EPT on age, all of these are estimated. But same as in male, the age, okay, the inference of age is not significant. Yeah, you can also copy those numbers and do the comparison between two groups. And the covariance means, yeah, the residuals. So you can see that the result tables are doubled. Previously, we only needed to know these parameters. Okay, but after we consider different groups, multiple groups, then the parameters are doubled. So that's why you cannot handle too many groups. Otherwise, the number of parameters will just too many. Okay. And then for mediation analysis, again, we have group of male and also female. So for male, we have the specific indirect, okay, specific indirect 1, 2, 3, direct effect, okay, and total indirect and the total effect. And from H to EPT, okay, all of these are reported. So for male, we have the mediation effect analysis. So all the effects are reported, okay, indirect effects. For example, from EDU to HVLTT to EPT. So for example, in this path, so here, specific indirect 1. So from EDU to HVLTT to, so this path, indirect effect, mediation effect, this path is reported, and again, for male, it's reported here. This is the estimate. So the product of these two coefficients, okay, this coefficient and this coefficient, the product of these two coefficients are reported here, and the standard error is reported here, T ratio, and the probability, the p-value is reported here. So it is significant. From EDU to HVLTT to EPT is significant. Specific direction, indirect 2 is EDU to R to EPT. Okay, so that means this mediation effect from here to here to here. The estimate here, standard error here, ratio and probability is still significant. Okay, so this is significant, this is significant. We also have 3. Okay, so from EDU to HVLTT to R and then to EPT. Okay, so we have here, 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 here. And it's significant. So we have this indirect path. Education level gonna influence your memory ability, then this will influence your reasonability, and then it will influence your daily life problem solving scores. It's also significant. And of course, we have direct from EDU to, it's also significant from EDU to EPT. This direct path is also significant. So all of these are partial mediators. So that's for male. Female, yeah, we have the result reported here. Okay, so, and of course, you can also investigate the age. among male and female. Okay, so all of these tests, okay, will be reported. These are significant. Which one is not significant? Okay, so let's see. All of these are significant. This one is not. Okay, so this one is not significant. From age to EPT for male group. Age to EPT. So this path is not significant for male. Let's see, female. It's not significant. For both, okay, male and the female, the age, the influence of age on EPT is not significant. For education, yeah, it's significant. It's significant. So that's a mediation for different groups. Yeah, actually, I did the comparison here. I did the comparison. I copied the results here. Male and female. I just used some part of the result. This is for male, for female, and EPT, okay, for male. Okay. So far, any question? Any questions so far? Good. And this is not significant. This is not significant. And we can, here I have some columns. Okay, so here we have overall. What does that mean? Suppose, ignore the grouping variable. We just group them together. Without the gender variable, we can run the data analysis together. Okay, so we have the overall report on all of these tests, like the standard deviation and t-value. And then you can compare these three groups. Yeah. So it's kind of like the average of these two, but still you need to consider sample size because the sample size for female is larger than male. So it's not exactly the average, okay? It's, yeah. And if you here, it's between these two numbers. No, here. No, it's not. Let me see. R on EDU, this value is 0.5, but for male, it's 0.4. This is 0.48. So how come if we run the overall, R on EDU is larger than both coefficients, vector loadings? Yeah, so how about overall? What is overall? So let me just give you another code. Downloaded from the LC and okay, so let's see. Let me open the code. So here, we do not have gender included. So this is overall without multiple group analysis. So the gender variable is not included in the use variable because I don't do any distinguish between these two groups. I just ignore that variable. And R is still observed because R is defined as a mean of the three. And the model, okay, so here, look at the model. We don't have the model for female, okay? Here, we only have one group, just one model. That's it. This is the overall, okay? And then in the very beginning, we don't have gender because this is a comment. Okay, this is a previous one, so I put a comment. Then this one is not key. Instead, I have these variables, and try to run the code. And now let's look at this output. Okay, number of groups, 1. In this case, 1. Sample size, okay, number of observations, 1,114. That's it. We don't do any distinguish between these two groups. And yeah, you can copy the results and do the comparison among.
If you wanted to break them up in ages by groups, is that
That's
something
good.
that you
That's
could
also
do that?
good. Yeah,
So if
you
you
can
have,
consider, but these are for elderly people. If you have some experiment, young children, okay, so less than 10, and another group larger than 70, it's very good to end up between maybe, I don't know, maybe 20 to 50 and 50.
Yeah.
Yeah, you can do
Okay.
this.
Thank you.
Yeah, that's good, yeah. So let's check what is yeah, okay, so for R on EDU, okay, let's see R on EDU. It is true. So the R on EDU is 0.528. Okay, so let's look at this column. It means, okay, so for overall model, the reachability on EDU is this number, but this number is larger than male and female. If we separate these two groups, male and female, so the estimated number is less than this value. Okay. It's interesting because it's kind of like a balanced consideration of all parameters. So this one is obviously not between these two numbers, It's larger than these two numbers. But look at the other. This is between these two numbers. Or this one. Okay, this one is also. This one is less. Oh, maybe here. Okay, this one is always less than each group analysis. This is one less than. But it's okay because the difference is maybe not significant. And age, okay, HBLTT on age and EDU. It's between these two numbers and EDU. It's also, yeah, it's also always less than these two groups. And I just copied the all results here. Okay, so this is overall. And then highlight this one. This is overall. This is group male. This is male. This is female. They are quite similar, but actually they are different. Okay, the actual numbers are different. But the significance, the p-value, I mean the p-value, the significance is quite similar. Okay, any question? So here we didn't do any test. I just show you, okay, so that's how we do the multiple group analysis. But you can also do specific tests. Suppose, yeah, so this is a review slide actually. So we have two models. A full model, suppose it's M2, a reduced model, or a model with constraint. Suppose, say it's M1, model 1. Then we're gonna calculate the chi-square values of each model and calculate the difference, okay? Of course, you have two ways. You can start from M1 and then free some parameters. Okay, so I'm gonna freely estimate some parameters. So the number of parameters will be larger, so we get M2, okay? And then starting in M2, I put some constraint, fix some values at some value, fix some parameters at some value. Then I get M1. So you can have two ways to do the test. But finally, you're gonna compare their test square scores, test square difference. So, for example, we're gonna assume all the parameters for two groups are the same, because after we do some comparison, we see that the difference is tiny. So why not assume these two groups are exactly the same? Then that is a reduced model. The full model is that okay, all group parameters are different. Then we're gonna compare. If the model between these, if the difference between these two models are not significant, they are quite similar, then we can just use a simplified model by assuming male and the female are quite similar. They are the same. We can use that simpler model if these two models are not significantly different. So how to assume some parameters are the same, then we can use this code, okay? Remember that in the previous analysis, we can give a parenthesis, a name, okay? We can give a name on some path. And with that name, with the same name, actually, it is the same parameter, okay? So if we use this code, then the result here, okay, results are reported here because I have already copied them one. For male and for female, if you check the results, the numbers, they are exactly the same because we assume that these tests are the same. Okay. So this is the code, okay? So I'm gonna assume that male and female performs exactly the same. This is one model, okay? This is one singular model. So the model from here to here, I just give all the tests a name. So all of these are given by a name inside the parentheses. Okay. And also we have the main part. The bracket means the main part, inside part. These are tests. Yeah, so let's just run this code. Assume that the parameters are same across two groups. So nothing new. I just give a name for each of these parameters. Okay. Each of these parameters, I assume that they are the same. By doing that, we just created a restricted model or a reduced model. So you can highlight, you can run this one and so still here we have gender, we have two groups. We have two groups, number of groups is 2. And sample size for each group here are reported here. And we have, yeah, basic part. And now let's look at number of free parameters. In this case, we only have 20. But remember, if you have two groups, that's 40, okay, because we doubled it. So if you go back to have the different, okay, so this code just report two groups parameters. So let's check here. The number of free parameters is 40. We have two groups. We assume all the parameters are different, totally different. But now it's 20. Okay, number of free parameters is 20. Why? Because we assume that female and male share the same parameters, the same value. We don't double the number of parameters. So that's why it becomes smaller. And the chi-square value, you can just copy the chi-square value here, okay? And we can copy the chi-square value of the previous model. Model results, okay. Now let's look at RMSEA. Although there's no factors, okay, but we put some constraint. We force some value are the same across male and male. We put some constraint. So that's why RMSEA here, it's not 0 anymore. Based on this value, actually this is not good, okay? So this value is too large. Also this value is too large, too big. And this is not 1 anymore. We just assume that male and the female performance exactly the same. This is not a reasonable assumption. We can see that these are not good. Okay? And then the results are reported here. And the mediation effects are reported here. Okay? For group part and for EDU part. Okay? And they also give you 2 plots, group male and group female. Group male and group female. But if you do the comparison between these 2 plots, they are exactly the same, okay? Because we just assume. So you can just copy these numbers and compare. Okay? They also report 2 groups of results. Okay? For female here, for male here. Yeah, just look at the slides. I have already copied them for you. I didn't copy the results for this one. Just copy the small part of the results. Okay. Yeah. So let's look at the chi-square values. So chi-square values. These are previous chi-square values. Almost 160. What about the previous model? Okay, good. Then the difference is here, and the difference in the degrees freedom is 20. So what's the chi-square value for 20 degrees freedom? So let me just do. Okay, let's have it. 31. Okay, so the critical value for chi-square distribution with 20 degrees freedom is 31, but here this number is large, much larger than 31, so it is significant. So what does that mean? So one model with male and female are all different parameters. The other model, reduced model, assume that male and female perform exactly the same. After we do the chi-square difference test, the difference value is 159, and degrees freedom is 20. The critical value of a chi-square distribution with 20 degrees freedom is 31. So then, what's your conclusion? Based on these numbers I just reported, what's your conclusion?
There is a difference.
Difference between what?
Men and women, or the 2 groups.
difference between other models. Exactly. Difference between two models. So which model should we pick? Which model should we keep?
The two-group model,
Why? The answer is correct, but why?
because of the chi-square value.
Chi-square value what?
It's more significant, it's larger.
Larger than, yeah, just complete,
Then the-
just try to complete the whole sentence, okay? Yeah, because, okay, that's good, okay. Because of the significance, because of the chi-square significance test, tell us it's significant, larger than the critical value. Means what? Means
The other model is significantly worse.
which one is significantly worse than which one?
The single group one.
The single model is worse than the two-group model.
Exactly. So that means the reduced model is a similar model by assuming that male and female performance exactly the same. Is significantly worse than the full model without this assumption. So we're gonna keep the two groups. Yeah, you're right. Two group model. By allowing that male and the female have different parameter estimates. That's a more reasonable model. Okay, that's good. Okay, that's good. So that's a result from this comparison. And then we can also do a specific test. So we just concluded that the model with assuming male and female is the same, it's not good. Then just assume these two paths are the same, or one single path is the same, but the other parameters could be different. Just focus on some specific paths, for example, R on H. We can just assume that H. So this one, we're gonna compare H inference on the reasonability is same or not. This path is same or not across male and female. How are we going to do the data analysis? Again, we're gonna put a name on this path. If we use parentheses with a name, that means, okay, I'm gonna assume this path is exactly the same for male and female. But the other parameters, for example, other parameters are freely estimated. I don't care about the other parameters. They could be different. That's fine. But for this one, and for this one, because here in this code, I assume that these two paths are fixed as the same. I'm gonna just test these two. Of course, you can just pick one. Okay, pick anyone or pick this one. Pick one. It doesn't matter. Just depends on your research question. So this is a reduced model. This is a full model. So let me give you the code of this. Okay, so download the test. Code for text. Okay, here. I put some comment here, and you can just freeze. You can just freeze this statement, or yeah. So these two are the same. So you can free this statement by putting this as comment, or you can just free this one. So you have to choose one from these two. Okay. So in this case, by using this statement without using statement, then it's full model. So we have full model. Again, here it's full model. But if you change the notation, so if you put a comment on this statement, free this statement, put a comment sign on here, that it's a restricted model because we assume that the path here is the same. So if you just run the model here, it's a full model. But if you remove the column sign, this one here, remove the column sign here, then we're gonna, oh, there's another one. So yeah, you can, because there's a lot of models. You can test D, or you can test C, you can test H, or you can test them together. So suppose this one,
See, this is what mine's gonna be looking like, all these different groups.
yeah, so I'm gonna, suppose I'm gonna common. So yeah, we can modify your code a little bit. Oh, actually, I'm sorry, there's another statement. Let me just go back. So we can just yeah, you can modify the code that you wish. It could be different models. This is the result from one model. Yeah, let's do the comparison. I already copied the result from both models. So for model one, suppose this is model one, reduce model. I'm assuming D and H are the same for female and male. For model two, okay, so D and H are totally different. So DH is R on H. Okay. Let me put it red. Okay, let me put it. R on H is D. This one. The EPT on R. Oh, I didn't copy all the results. Okay, so just check the model one by assuming R on H is the same. So after I put the name on R on H, that check the result. Okay, the estimates are exactly the same, negative 0.144, and the standard error ratio, p-value, these are exactly the same. But if we free that parameter, okay, so R on H, this is reported here, R on H. For female, it's reported here. They are different. These two are different. These two standard errors are different. Ratio different. Of course, p-value is the same. Then let's do a comparison between this model and this model to see if this constraint is reasonable or not, if it's a good assumption or not. Okay. So if we assume that D and H are the same, the chi-square value is this one, equals freedom, p-value. For the full model, by allowing these D and H paths are different for male and female, then the chi-square value here gives freedom p-value. So what's the difference between the chi-square values? Yes, this number. What is the degrees freedom difference? 2. Well, let's check the critical value, okay? Let's check the critical value. 2. Almost 6. Okay, 5.99. 6 is a critical value. Then, what's your conclusion based on the result here? What's your conclusion? It's not different. That's not significantly different. That means what? Means what? So, which models we are comparing?
Reduce and full model.
Reduce and full model. So, based on the
reduced model is the best.
okay, she said the reduced model is the best.
No, reduced model is.
I'm gonna say that you're right. Okay, so we're gonna keep the reduced model, but the reduced model is not better than the full model. Still, the reduced model is worse than the full model, but it's not significantly worse.
Yes.
It's just not. It's not good as full model, because full model have more parameters. Okay, if we have more parameters, usually okay, the model fit will be better. But the difference is tiny. The
Statistically.
yeah, statistically not significantly, yeah, worse than the full model. But based on the rule polynomial rules. Yeah, so we're gonna keep the singular model. So we're gonna keep this model. So this model actually is with a smaller number of parameters. Okay. So we can assume that D and H, so D and H here, we can assume that the inference of D and H, I forgot. So it's from H to R, or maybe EDU to R. So which one? EPT on R, EPT on R. Okay, this path and this path. So we can assume that this path and this path are exactly the same for male and female. You can do that because the difference is not significant. It will not change your model largely. So it's a reasonable assumption. Yeah. It's a reasonable assumption. Any question? And of course, you can just test one. You can just test one path, okay? By putting one name, or you can test this together. Okay, you can just add more paths, and that's good. Question? So that's how you do multiple group analysis. Okay, to test. Okay, to see if that factor or if that variable influence the other variable same or not across different groups. Yeah, so for model 1, we assume that D and H are the same simultaneously for male and female. Okay. The chi-square value discrete. For model 2, we allow they are different D and H, okay, for male and female. Chi-square value discrete. So the difference is here, the p-value is here. So yeah, there's no group differences in D and H. Yeah, this is an exercise for you. So I ask you, so if C, so C is actually in the code. I already gave you the C here. So the C, this path. So this is a C. I want you to do the test of C, okay, only. EPT on H, the inference of H is the same or not, okay, for me and female. So that's an exercise. So yeah, this is an exercise. You just use the time to very quickly just conduct the analysis. Yeah, you can just see your results. Of course, I have already reported the result, but you can just obtain it by yourself. So this is for C.
So what now you really do is remove the D and the H.
Yes, you're right. Okay, we're gonna remove D and H. Yes, you're right. Just follow your suggestion.
Sorry.
Yeah, that's good. So remove D and H and then allow this one.
Take off that exclamation.
Yes.
Yep.
Okay, then that's a code. So we can run.
Sorry, I don't have N plus up, so I can't do it.
Oh, okay. Oh, okay. Yeah. So we have the result reported here. And chi-square value. The chi-square value. This is the chi-square value. And this model gonna compare with the model.
So we always want to use the chi-square for the model fit, not
Because
for
they are nested.
not for the base thought model.
No.
Bless you. Bless you.
I'm sorry.
You're fine.
Just ignore the baseline model.
Sure.
Baseline model is the worst model.
Good. I
Yeah.
did.
Baseline model, don't just, yeah. You don't need to look at this part because where's the baseline model?
I don't know if it's in there, but I saw it in the homework.
The baseline model, yeah. This one is a worse model, so don't do anything about this part. Okay. So this is a where is that? Okay, yeah, no. So no, it's not here. Okay, it's here. Okay. But anyway, baseline model is always worse, and yeah, worse more. Okay. This is the chi-square. Where's the chi-square?
The model fit you were just
Yeah, yeah. This one. Yeah, you're gonna copy this number and then compare it with this value, okay? The two groups. This is a two group analysis by allowing all the parameters are different. But here for this model, we assume that the C path is the same. Okay. And then this is the result, okay? For reduced model, for the full model, degrees freedom 1. So the chi-square for degrees freedom 1, the critical value is 3.8, okay? So it's less than the critical value. It is not significant. So the reduced model is not significantly worse than the full model. We should use a reduced model because it's similar. So we can assume the C path is from EPT or H. Okay, it's from H to EPT. So it's H to EPT, this one. Yeah, same. You can assume that the inference of H on EPT is the same for male and the female. You can totally do that, yeah. Yeah, the cutoff point of chi-square critical value is here, 7.8, and the difference is here, this freedom is 1. Yeah, there's no difference. See. Question? Good. Then let's have a break. This is session 1. Yeah. And next session, we're going to apply the multiple group analysis to the real measurement. Okay. And there's a huge topic. The topic is called measurement invariance. So when we have, just like in your case, you design some questionnaire, you're going to make sure the measurement is invariant across groups. You cannot say, okay, those questions are good for male, but not good for female. That's not a good design. Yeah, so you're going to use a multiple group analysis to make sure your measurement is great. It's invariant across many groups. Yeah. Okay. Okay, let's have a break, 15 minutes. Okay, so let's look at the second part or the application part. So it's called measurement invariance. So, or it's also called measurement equivalence. Okay, so it concerns whether scores from one operationalized of construct have the same meaning under different conditions. Okay. So it could be changed. If you have different populations, the score could be different. If you have different time of measurement, for example, you give a test in summer or you give a test in winter, maybe the scores will be different. Okay, or today or tomorrow or some different time of measurement, scores might be different. Or methods. Okay, so for example, computer administration or paper and pencil format. So I think there's a famous example in Twitter. So I think which year I forgot. So one researcher just used the exact same items from paper and pencil formatted to online. So he just wanted to try to use the computer test, but he found that the scores are dramatically lower than the paper and pencil format. But the items are exactly the same. The questions are exactly the same, but just different format. And then finally, he figured out that because of the time limit, so for paper and pencil, so for one item, the people can use a lot of time on one item and the other item. But for computer administration, so in the very beginning, so he just gave a very limited time for each question.
So these kids maybe just cannot finish each question within the time period. So the scores are lower than the other format. So it is important, okay? And the next slides are actually based on the paper of the paper on psychometric. So you can just download the paper and look at the online here. So we have, this is a quite old paper, okay? It's called the Measurement Invariance Factor Analysis and the Factorial Invariance. Okay. So it's from Berkeley and it's quite old paper. They just give a lot of definitions, formulations, and test methods. So this is a good paper. So you can just follow, follow instruction clears introduction, formulations, and the formulation, they give some notations and the meaning of these notations. I summarize this paper by using slides. Okay, so suppose starting from the formulation, so we have to give some terms or definitions of this area. So suppose we have different different variables, different notations. The variable x denotes the observed variable. X denotes the observed variables. And the variable w denotes the latent variables that can be measured by x. So what does that mean? So x here are our test scores. W are our latent factors. Okay, W are latent factors of x. Okay, x could be test 1, test 2, test 3, test 4. W is the latent variables we are trying to measure. Okay, and we also have V denotes variables used to classify different subpopulation or different groups. Okay, so we have different groups. We use V to show that is a classify, or that is an indicator or group indicator, or it's just a class variable. Okay, and we also have F. F is a function. Okay, it's a cumulative function, cumulative distribution function. Then he trying to use F function like this format. Okay, so we have F. This is a CDF. This is a cumulative distribution function. X is observed variable. Okay, which based on latent variable. Okay, W is a latent factors, and based on that group variable. Okay, for different group, based on different latent variables, the observed variable, the value of the X will be different. And let's try to look at the F. Okay, so the random variable X is said to be measurement invariant. Okay, so this is definition. If that is said to be measurement invariant with respect to selection on V. So V is a grouping variable for different value of V for different groups. If X is a measurement invariant, what's a conclusion? What's a condition? The condition is this equal this one. Okay, so F of X based on W and V is the F of X based on W without V, because inference of V is not important here. Okay, so for all these sets, okay, so we have X, W, V sets in the sample space. So the inference of V is the same for all sets. That's called the measurement invariant. This is an example. For example, we take V, okay, V as gender. Then we have male and female, 2 values for V. We have 2 values. And what is X? Suppose this is a math test scores, what we observed test scores. What is a W? Is a latent math ability. Latent math ability gonna influence the students' test scores. And the function has 2 groups, male and female. So if that function CDF of this one
test score based on methodology. For male, A, SEM, F for female. Then we say that the math test score is measurement invariant with respect to gender. Because it's as I say, for different value of weight, for different value of gender. The function of the CDF of math test based on methodology is the same. So it is measurement invariant with respect to gender. Yeah, so the random variable X is measurement invariant with respect to selection on V. So that means, okay, cross groups. If it's measurement invariant, if and only if X and V are locally independent when conditioned on W for all W in the sample space. Okay. So those are from that paper. So these are conditions. Okay, if and only if X and V are locally independent. X is observed variables. V is our grouping variables. And if X is measurement invariant with respect to selection on V, then this is true. Okay, this is true. Actually, this is quite similar as the previous definition. Okay, this is a detailed form of the previous submission. So what is S? S is a value of V. Okay, so we have S is a function in V. So different group is S function. Okay, for all these space. Okay, all these three variable space, and then this is the sample. Okay, where this is the conditional dispersion function for the subgroup S. You can think about this is male or female. Okay, condition on male. What is F of X? Okay, V and W. What is a function based on female? Okay, so these are conditional dispersion function for the subgroup S. Given any two selection functions, for example, S or T, you can just think about, okay, female and male, we have two functions. So these two are the same, okay, based on S or based on T, as I said, for all W, X and W. So here, so he trying to improve that in a math approach. So it's very important that for all W and the X and W, okay, so sometimes it's true for some specific X and W. That's still not measurement invariant. So you have to show it for all W and X. If this equation is true, then that is measurement invariant. Okay. Okay, so let's try to understand the difference of these types of measurement invariance. Okay, so we have different types of invariance. The first one is the simplest one, or the beginning of the test. It's configural invariance. Okay, it's very rough comparison. And then we have strong factorial invariance. We also have strict factorial invariance. We have weak measurement invariance. Okay, so finally we have the measurement invariance. Measurement invariance actually is very, very strict. So we can have some previous steps to have this test. So first one, factorial invariance or factor invariance. So it's based on our factor model. So this is our factor model. So we have X here, intercept, we have the latent variable Z, and we have factor loading matrix, lambda, and we have a residual. Okay, so observed variable, latent variable, and a residual. Okay, three parts. And Z and U. Okay, Z is a factor, common factor. Okay, Z are common factors. U are unique factors. We assume that they are independent. Okay, these are our common assumption in factor model. Common factors Z and unique factors U are independent, are uncorrelated. Okay, are uncorrelated in population. and the mu are mutually uncorrelated in population. What does that mean? So all the residuals are independent. So we have U1, U2. Okay, for each, for example, for X1, we have U1, for X2, we have U2. So they are mutually uncorrelated in population. They are not, okay, they are not correlated. They are independent in the population. That's the assumption for U. Then from that model, we have the mean of X, the covariance of X. So these parts are derived from the vector model. Okay. So we have vector model described here. Maybe I should delete the dash here. So this is like annoying. It looks like a minus sign. Actually, these are not minus sign. So that is our model. This is actually the mean part. This is just covariance part. So we have expected value of X, okay, mean part. Then it's expected A, okay, plus expected Z part, the latent variable. And of course, we have the lambda matrix, expected U. So we assume that the residual part of the expected value is 0. That's our assumption. And it's constant, so it's just A. And this one, we assume that this is mean. Okay, we assume the factors have mean M. Okay, this is mean M. Then we have the mu. This is, we assume mu equals A, okay, plus the mean of factors, mean of Z. Z is latent factors, times the factor loading matrix. Oh, here, this is, okay, this is eta, so we assume this is eta. We can assume this is eta, but usually the eta is 0, but whatever. Okay, so the U, we can assume that is, the mean part is eta. Okay. And then this is the covariance part. This is the covariance matrix of X. We use capital sigma. So we have X, okay, we have A here. The covariance of a constant is 0. Okay, we don't have anything here. And then we have the covariance of this part. So covariance of this part, so we use a matrix rules. Okay, we have lambda and the covariance of the Z and times the lambda transpose. And also the covariance between the U. Okay, there's no covariance because Z and U are independent. We do not have any covariance here. So this is 0. So this part is 0. No covariance. And then we assume the covariance of Z is phi. Usually we assume the phi is the covariance matrix of latent factors, just like our homework 5. Okay. In homework 5, you're gonna estimate the mean. Okay, the mean of the parameters. Okay, we have intercept, we have slope, or we may have projector. So the mean part. And then we also have the phi part. Phi, usually we assume the phi is a covariance matrix of latent factors. Latent factors in our homework 5. It's intercept, slope, and projector. So this is just the covariance matrix of our latent factors. Okay, it's intercept, slope, or projector. Okay, and the psi is a covariance matrix of the unique part, the unique factors. Okay, so this is the covariance matrix of the U. Okay, U1, U2, U3. So it's usually it's a diagonal because we assume that they are mutually uncorrelated. So that means they are diagonal. All the off diagonal elements are 0, 0, 0. Okay, then we have psi 1, 1, psi 2, 2. We have psi, yeah, so we have psi, depends on number of items you use, okay? And in the homework 5, we have 5 waves, so we have 5, 5, okay? And this is, yeah, 3 parts of the output parameters in homework 5. So same thing here. We assume the phi is a covariance matrix of latent variable. Here is Z. Then we have phi here. So it is lambda times phi transpose of lambda. This is a psi, okay? This is the covariance of the residual part, okay? Covariance of the residual part. This is psi. And the plus psi, okay? That's it. So this is the second moment. This is the first moment, okay? If we have mu, we call it first moment. Second moment, of course, we can continue third moment, the fourth moment, but that's too complicated. So what's a configurable invariance? Okay, previously just review of our vector models. Configurable invariance gonna focus on the lambda matrix. Here we have lambda matrix, we have lambda matrix. We want to make sure lambdas are roughly the same across groups. Okay, lambda. We take a configurable invariance to mean that the same simple structure exists in the subpopulation, in the sense that, okay, first, 0 elements are found in the same locations in lambda, in several subgroups studied, and that too, okay, homogeneous, okay, homologous non-zero elements all have the same sign across subgroups. So let me just try to use this. Okay, so we want to make sure these 2 parts, 0 and the non-zero, okay. If it's 0 elements, then you have to make sure across subgroups, okay, subpopulations studied, we have the same 0 elements. If it's non-zero, you also want to make sure they have the same sign. If it's a positive or it's negative, you have to make sure the lambdas are the same in several subpopulations. Yeah, so that is the same simple structure for all groups. They have the same 0 loadings or non-zero loadings, have the same sign. So let me give you a very simple example. So it looks like it's complicated, but actually it's very simple. So suppose we have 2 groups. Okay. So lambda, we have 2 lambda structure. Let's say the lambda for male and female. So we have lambda for male. Male that, I don't know, suppose it's 5 elements, 5 by 2. Okay, so we have some elements here, some elements here. Just 4 by 2. So this is a lambda for male, and we also have the lambda for female. Same thing. Okay, we have 4 by 2. What does that mean? For configurable invariance, if it's 0 in one matrix, lambda matrix, you have to make sure it's 0 in the other matrix. Suppose this one is 0, okay. Then you have to make sure this location, this is also 0 for different groups, for female and for male. And we can also assume this is 0. Suppose this is 0. Then you have to make sure this is also 0. And if it's non-zero, this is non-zero, then you have to make sure they have the same direction, same sign. Suppose this is positive, a number which is not 0, then they should be positive. If it's positive for a number, then you should be make sure it's positive. Okay. And if it's positive, it should be positive. But now here, if it's negative, some negative number here in this location, then you have to make sure this is negative. Okay? If it's negative, then it's negative. If it's positive, then it's positive. So you just check 0 and the sign of non-zero numbers. This is the first step. Why? Because if you have different signs, for example, suppose here, you have positive number here, you have, which one? Okay, here. If you have negative number here, it should be negative. Suppose this is positive, then these are different lambda matrix. These are different. You cannot say that these two groups are the same. The sign is different. So you should not continue to check the measurement invariance across these two groups. So if it's negative, it should be negative. So this is step. Very beginning, we just want to make sure the same sign, so the same loading, same zero loadings across groups. Okay. And then we have another stronger invariance test. It's called strong invariance. What does that mean? We're gonna, in addition to the lambda matrix, we're also gonna check the intersects. So in this step, A and lambda are our focus. So if X is strongly factorial invariant with respect to V, selection of V, then the mean part and the covariance part. So this A intercept, okay, intercept and the lambda matrix should be the same. Okay, so we have these two components. So for lambda, in addition to the first step, the sign and the zero elements, you have to make sure the numbers are quite similar, okay? Same lambda and same intercept. This is much stronger than the previous step. Previous step, we just very simple. Okay, now we have lambda and A. And we can move forward. So if you satisfy, okay, these are different models. You have to make sure the previous model is satisfied. Okay, if this condition is satisfied, then move forward to test this one. If the first step failed, if you cannot make sure the signs are safe across groups, then just stop here. There's no need for you just do the continuous test. So if this test is passed, then do this test. And again, if this test is satisfied, it's passed, then do the strict. Because strict have more conditions for you. In addition to lambda and A, we also have psi. We have to make sure that residual variance are the same across groups. So it's more, there's more conditions for you to do the test. And also, if you want to check the E and the W, okay, so if X is strictly factorial invariance, X is almost certainly weak measurement invariance. And then, what is a weak measurement invariance? You have to specify these two moments are the same. Okay, so the first moment and second moments are exactly the same. Then you can say that these are weak measurement invariance. So we have different steps. So we just show you these models. So first step, fit the model separately. So you have the, again, we're trying to use a male and a female example. So run the model for female, run the model for male, and then look at the lambda matrix. Check the signs, okay, and also check the zero elements. Okay, if they are the same, then they share the same simple structure. Then we have the configural invariance. Okay, that's first pass done. If it's not the same, just stop. Okay, you are not qualified to continue to go to the second model. Yeah, first step. And then if it's satisfied, then go to the second one and try to fit the multiple group model with the same factor loadings. So what does that mean? Just apply the previousness. We have to make sure the loadings, factor loadings are the same. By putting some constraint on all these loadings. Do not constrain on the other parameters. This part is only for the factor loadings.
for residuals or for intercept, no, you don't need to do that. But you have to make sure that you put the constraint on factor loadings. Run the model, do the chi-square difference test. Okay, chi-square difference test. If the model fits well, then if they satisfy this condition, then it satisfies it has a strong factor invariance. Otherwise, okay, if we figure out these two models are significantly different, then just stop. The lambdas are different. Just stop. Okay, you don't need to do the other test. Okay, if the strong factor invariance satisfies, then move forward to test a strict factor invariance. In addition to the factor loadings, you also have to make sure the psi, the residual, the variance are the same. So put all the residual variances the same. Just use the parentheses and name. And run the model. That is another new reduced model. And then check the difference, the chi-square difference, okay? If they are significantly different, stop here, because they are different. If they are not significantly different, then continue. Yeah. So just start from the simplest one and eventually test lambda, test the psi part. And you can also continue to test the phi part, the variance of the factors. Okay. Test the mean part, the mean of the factors. So you can just continue. If you check all of this, then the expectation and the correlation matrix will be the same. Okay. But usually you cannot go very far. Okay. Usually you can just stop somewhere here. It's very hard to pass this test because these are too strong. Okay. So let's look at the example. So now it's, yeah, we can just continue next week. It's okay. So we have again, this is all the data. So we have some students from P school, okay, past school, and some students from GW school, Grand Y school. And so they are, in the original test, we have 26 tests. They are trying to measure the people's spatial, verbal, mental speed, memory, and mathematical abilities. So suppose that we're gonna test a verbal and the memory test for this example. So these are items. Okay, these are items. Paragraph, what is that? Okay, so sentence and the word C and the word M is a verbal test. And the word R, memory R, object, and the figure W are memory test. Okay, verbal test and memory test. So we have 4 here, we only have 8 tests in this example. Okay. So we have 4 here, 8 tests. So original names have a large number of variables here, the original names. So we're gonna take this 8. And here we have, this is okay, use, observe. What does that mean? Okay, we have 2 schools. School equal 1, the school equal 2. School. So we have school actually it's included here. Okay, although school is not in the user variable, but we can just pick some observations from particular schools, from P or from GW, from Pastel or from Grand Y. You can use this statement to pick your special observations. When school equals 1, then it's from P school. So the analysis, it just focuses on that specific school. If school equals 0, then you're going to use the other student's variable, okay? And you can just rescale it. Okay, this is also a trick. If some numbers are too large, large, or if some item test scores, okay, too small, you can rescale it. Because when you do the data analysis, if the data are unbalanced, some numbers are extremely large, some numbers are extremely small, you may have some error messages. So those are tricks. You can just rescale your number. So this is divided by 4. This is divided by 10 to make the numbers are relatively balanced. Suppose variable 1 is 1,000 or 2,000 or something, okay. And number 4 is 0.002 or 0.5. So these are not very balanced. You can just make some numbers larger, you can just make some numbers smaller by rescaling these numbers. So this is one way to define the new variables. And then that's it. This is our model. Okay, we have memory factor, latent factor. Here, this is a factor model. This is not average anymore. This is a factor. Okay, memory is measured by these 4. The verbal ability is measured by these 4. So this is factor models. And then we're gonna check the lambda. Okay. So we have 2 schools. We have PASS school, P school, and GW school. So we just pick the PASS school. So when here, so if you use a code, when school equals 1, okay, when school equals 1, then you have the information in the first row. When school equals 0, then you have information on the second row. So this is a combination of 2 model analysis. Okay, so we have chi-square obtained from the first school. Degree freedom, p-value, okay, RMSE, SMR. Okay, we have the chi-square value from the other school, from the GW school. We have the result reported here. And also for the memory factor loading of memory, 1, 2, 3, 4. We have 4 indicators. By model identification, we assume the first factor loading is fixed at 1. They fixed at 1. So you don't need to compare this one, estimate this one. And then this is a lambda for number R. This is number lambda for object. This is lambda for figure W. And then we have the other lambda values for the verbal latent variable. This is for the memory. And again, for the first row is from P school. The second row is from the GW school. The question is that we want to make sure the factor loadings are the same or not across these 2 schools, okay, P school and the GW schools. So if you have the result like this, what's your conclusion? Is there any configurable invariance between 2 schools? Between P school and the GW school? Is there any configurable invariance? Any idea? Any thought? Configurable. Think about configurable. You only need to check 0 and the sign of non-zero numbers, okay, factor loadings. So here I put small star, okay, little stars, asterisk. What does that mean? It's significantly different from 0. So that means these are not 0. All of these factor loadings are not 0. Then we should check the sign. Sign of this one is positive. Sign of this one is positive. Positive, 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 positive. All of these are positive. The sign is safe. Then what's your conclusion? Is there any configurable invariance between the 2 schools?
Positive significant difference.
Is any, so yes or no, the answer? Yes or no? Yes or no? Is that difficult?
The question was if there's
Configurable invariance, is there any configurable invariance?
like any kind of big differences between the 2 schools.
Yeah. P school and the GW school, yeah.
Well, if you look at the object between the two schools is almost double.
But I said, but I just said
Yeah,
direction or sign for the first step.
no, they're all positive. They're all the same.
Then, yes or no? What's your answer?
No. 50-50.
Invariance means it's not very.
It's yes, because all the signs are the same across two schools, yeah. Across these
Shot in
schools.
the dark.
Yeah. Okay, good. So that means we're gonna move forward. That's good. We're gonna move forward. This step satisfied. And then we're gonna test two models. Okay, we're gonna compare two models. One is a two group model with all three parameters. Okay, lambdas are different. The other one is that, okay, we assume that the lambda are the same for these two schools, P school and GW schools. Yeah, actually, I give you some exercise here. So we don't have much time, so we can just leave this example next time. So we don't have much time. So you can just try to do it by yourself. This time, you're gonna compare two models. The full model, this is full model with two groups, two schools with all three parameters. So that means that lambda for P school equals 0, or lambda for the GW school could be different. The other model, the two group, okay, have the same lambda. Lambda for P school, lambda for GW school is the same. And then you do the model comparison. Yeah, so if it's significantly different or not, the chi-square value difference, you're gonna see. If the reduced model, by assuming they're the same, is significantly worse than the full model or not, okay? Okay, so we can continue this part next week. Yeah, okay. So that's for this class. Any question? Any question? We don't have any homework. Yeah. Oh yeah. So homework 5 is due today, and please go back to check. Okay. So if you have any homework, okay, if you want to resubmit your homework, or if you want to correct some mistakes, just let me know.
And that's all due by the 18th, for which is our Q&A day, right?
You can do it tomorrow. Earlier submissions are always welcome. Okay, yeah. So think about your course project, okay? And
Yeah.
check your homework scores. If there's any mistake I made, just let me know as soon as possible. And let me see. What else? Yeah, I will give you back the homework file next week. And I think that's it. And after 2 weeks, on April 18th is the Q&A. And after 3 weeks, on April 25th is your presentation day, but you don't need to come here. So just send me the recordings, okay, videos, yeah.
Thank you, ma'am.
Thank you.